Thank you for attending today's webinar, Enhancing Protein Purification Efficiency with Advanced Filtration Solutions. I'm Tristan Free, Senior Editor at Biotechniques, and I'll be your host for today's event. Before I introduce you to our speakers, I'd like to quickly cover a few housekeeping items. Firstly, all the information about today's webinar can be found on the right-hand side of your screen, including the Q&A tab. You'll have opportunity to submit questions to today's presenters by typing your questions into the Q&A box on the right-hand side of the window. You may send your questions at any time during the presentation, and you'll find all of your asked questions in that tab. Please note that other attendees will not be able to see your questions. We'll collect these and address them at the end of the webinar. If you encounter any technical problems during the webinar, please use the online chat support function, which can be found by clicking on your profile icon, navigating to the help desk, and clicking on the chat with support icon. Alternatively, you can contact us at clientprojects@tandf.co.uk for further support. Lastly, look out for 3 poll questions that will appear throughout the presentation in the right-hand side toolbar. An on-demand version of today's webinar will be available approximately 1 hour after the webinar and can be accessed using the same audience link that was sent to you earlier. So, we are delighted to have Dan McElroy, Karen Elbing, and Jake Brown presenting for us today. Dan is the Global Senior Product Manager for Lab Filtration at Cytiva, specializing in the syringe and syringes portfolio. With over 25 years in the life science industry, he has extensive experience in various roles, including field application support and product management. Dan holds a bachelor's degree in biology from Monmouth University. Karen is the Business Development Manager for EMEA at Cytiva, with a specialization in chromatography. Her extensive experience as an active sales specialist allows her to assist users in optimizing their chromatography workflows for efficient protein purification and analysis. Jake is the Global Product Manager for Laboratory Filtration at Cytiva. He manages the filter plates, centrifugal filters, and the 903 collection card portfolio. He has been with Cytiva for 8 years and holds a master's degree in molecular biology from the University of Nottingham. Thank you again for joining us today, everyone. I'll now hand over to Dan to start today's presentation.
Thank you, Tristan, for that introduction. Today from Cytiva, we're going to be speaking through enhancing protein purification efficiency with advanced filtration solutions. So we do welcome you to our webinar. Why is protein purification, and more importantly, the sample purification or the sample prep, so important? If you look at the picture on your screen, you can see, as we would say, this is your workflow or a typical workflow or the ecosystem. And as you can see, directly in the middle, of course, that would be the ECTA chromatography system. But both upstream and downstream, you will see opportunities for filtration. Now, these opportunities for filtration have many uses and benefits that I and my team will go through today, but the whole goal of this is to have better chromatography results using chromatography systems and including some type of buffer filtration. So why is filtration so important? Again, if we look onto the left side, these are the impacts of not filtering. You may see delays because you have to go back and do constant tests. Poor protein yield. Has anyone ever had poor protein yield? Yeah, it could be because of a lack of filtering or an improper filtering. Inaccurate results is probably one of the worst results that we could get from our chromatography runs, or having to use an exchange and go through multiple columns. The other reason or other issues that could be as a result of poor quality filtration, clogged tubings. Clogged tubings usually is going to give you directly decreased column life or damage to your system. When you have damage to your system, downtime, nobody wants downtime. The symptom of maybe a lack or inaccurate or inadequate filtration, the first thing you may notice is increased back pressure. So your system, your chromatography runs, they will give indications as to a potential problem that usually selecting a good or a specific filtration protocol will definitely be able to help you manage.
We've now heard that filtration is important for protein purity, yield, and function. So now let's shift our focus and take a closer look at how sample and buffer pre-treatment can help prevent buildup of high pressure in your chromatography system and columns. So where could the high pressure come from? It could originate from the sample or buffer, the column, the system flow path, or sometimes a combination of all of these. So next slide, please. So let's break it down and look at some of the most common contributors. Particles in the sample will clog the pre-filter column. Particulates in the buffer will block your online filter or cause the pumps to deliver an erratic flow. For removal, you can either use filtration or centrifugation. Sample participants are insoluble aggregates that will also block pre-filter and column. The precipitate can be removed by filtration, but there are also actions you can take to reduce aggregation, such as adjusting the sample conditions, avoiding mechanical stress, or prevent too high protein concentrations. And finally, at the bottom, if you have microbial growth in your sample, it become cloudy over time, it can clog filters, and you will also see a buildup of pressure on your column while loading your sample. And if microbial growth occurs in your buffers, it will look cloudy and your online filter will become blocked over time. So to prevent microbial growth, use freshly filtered samples and monitor your buffers, especially those containing phosphate. And in the upcoming slides, I will address the two first points in a bit more detail. So what can we do to effectively remove particulates from sample and buffers? There are two main strategies for this. You can either use filtration or centrifugation. Filters with low non-specific protein binding is recommended, such as cellulose acetate, regenerated cellulose, or polyether sulfone. Equally important as the filter material is to choose the right pore size to match the column you will use. For columns with large beads, use a 1 micrometer filter, and for medium-sized beads, 0.45. And for small beads, or when you need a very clean or sterile sample, then you would use a 0.22 micrometer pore size. If your sample is small or protein sticks to your filter, then centrifugation is also a good option. For general protein samples, you may spin at 10,000 G for up to 15 minutes. And for more complex samples like cell lysates, a higher force of 50,000 G for 30 minutes is recommended. So by following these guidelines, you can prevent particulates from entering your chromatography system, and this will also ensure a smoother run. So next slide, please. So as I just mentioned, sample filtration can be used to remove particulates from your sample to prevent them from entering the column, as this can reduce column lifetime and result in distorted peaks or cause increased back pressure. To demonstrate the effectiveness of filtering samples, we applied 6 milliliter cell supernatant containing a human monoclonal antibody onto a high-trap MAD-select Prisma column, with and without filtration. The filtered sample was prepared using a 30 millimeter syringe filter containing a 0.45 micrometer regenerated cellulose membrane. After the elution, the column was cleaned with 1 molar sodium hydroxide, visible on the chromatogram as a cleaning in place peak around 27 milliliters. And on the left, you see an overlay of the full chromatogram of filtered and unfiltered sample. The elution peaks looks similar for both the samples, but on the right, we have zoomed in on the cleaning in place step. The unfiltered sample show a much higher absorbance, which means more contaminants were retained on the column. This clearly shows how filtration helps keep your column clean and reduces the need for extra cleaning cycles and also potential blocking of ligand binding sites. This is an easy step that can significantly improve your column lifetime and performance. So the next slide, please. I previously also mentioned that protein aggregation and how it can cause high back pressure in the system. So to the right, you see a standard protein purification workflow, and this contains several steps, including overexpression of the target, sample preparation, for example, cell lysis, followed by one or several chromatographic steps. And after purification, proteins are usually stored until their final application. And throughout all of these steps, there is a risk that protein aggregation is triggered. What is then protein aggregation? It refers to the abnormal clustering of proteins into larger and often insoluble structures. And if we look at the left, we have listed some of the aggregate triggering events. So during protein expression, aggregates can form as inclusion bodies. These are dense, insoluble protein clusters that can complicate your downstream purification. During sample preparation, proteins can adhere to cell debris, leading to aggregation, and this can hinder the efficiency of filtration and any subsequent purification steps. Physical stress during sample handling or processing, such as vigorous mixing or pipetting, can also cause proteins to start clustering together. So gentle handling techniques can help minimize this. A change in ionic strength or in pH is also a major risk factor, especially if you pass the isoelectric point of your target protein. And finally, repeated freeze thawing might also induce aggregation. So just understanding these factors and implementing preventive measures, you can reduce the risk of protein aggregation. So next slide, please. So even if you have taken the preventive actions to minimize aggregation, it is still common that some aggregate removal is required. And aggregates are present both as insoluble and soluble forms. To efficiently remove the insoluble aggregates, filtration is commonly used, and we recommend using low protein binding filters, just like the ones I mentioned before. A commonly used working definition is that insoluble aggregates are retained by a 0.22 micrometer filter, while soluble aggregates pass through and remain in solution. The image on the left displays a protein prep filter, which is effective for aggregate removal of insoluble aggregates. For removal of soluble aggregates, there are several options using liquid chromatography. The most common technique is size exclusion chromatography, where proteins are separated by size, with the largest molecule eluting first. In the example shown to the right, the sample was loaded on a high-resolution SuperDex 200 column, and large aggregates eluted first, followed by the intermediate antibody dimers, and last the monomers. So now I hope that you all have a better understanding of what can cause high system or column pressure, and most importantly, what you can do to prevent this from happening to you. And now I hand over to Dan.
Karen, thank you for taking us through some of the most common back pressures or other issues that we can run into during our chromatography runs. What I did want to highlight on this slide is just all of the options or availability to introduce filtration either into your sample and buffer or filters that are already present on the system. Starting on the left bottom, centrifugal filters can be used to adequately have sample concentration in a format that is ready to load onto your system. If you have a little bit larger volume size, you can use syringe type filters. The column itself, there is a column on the top of the filter. Now, does it do all of the necessary filtration? No, it's more of a stopgap, or if there is minor impurities, it may prevent them from going into your column. By no means is it the only need for filtration prior to loading sample, but there is usually some type of a filter built onto the top of the columns from Cytiva. Following right next to that would be buffers and solutions. Whether you are preparing your own buffers or purchasing buffers that have previously been mixed and stored, we do recommend that you go ahead and filter those buffers, make sure that you have them tightly covered. Any material or debris that is in the airstream in your laboratory, in your environment, they are going to find their way into that buffer. So doing a good filtration prior to using buffers on the system. Karen mentioned fresh buffers. That's another correlation to fresh filtered buffers. If they've been sitting there for any length of time, having them run through another filter cycle is always a best chromatography technique. They can be many different formats for that type of filter. The image we're showing here would be a capsule filter or a larger disc filter unit. And then lastly, on the system, there are two built-in filters. One is the inlet filter. It is on the sinker, so that titanium sinker that drops into your buffer bottles. There is, again, and it would be a very wide or large mesh filter. Any truly large particulate would be trapped at that filter, but it is not meant to be a final filtration. Running your filter through a 0.2, 0.45, maybe even a 0.8 filter is always recommended, but we do place filters, inlet filters on those sinkers. And then there is a small filter that is in the system flow path. I believe it is pre-column, and that is known as the inline filter. Again, if you have multiple buffers coming through the system, that is an area where those buffers can truly be mixed and make sure they're homogeneous before flowing onto the column, and we do call that the inline filter. Both of those filters should be considered as a maintenance item, and you can easily talk to your ectochromatography specialist, your service representative, or local FAS from Cytiva for any help with that. The bottom line, though, is there are multiple areas and avenues that overpressuring or contaminants can ruin or come in contact with the system, and filtration can prevent or eliminate most of them. And this guide map will just help you understand the amount of filtration that really goes into and can be used inside of a purification run. So how do you know about what is the right filter select for your application? So there's going to be two main key points that we're going to look at. We're going to look at the pore size. Pore size would directly relate to contaminants. And then we're going to look at filtration volume. So if we go to pore size, as you can see in the table, there is a list of pore sizes. Cytiva has these plus many more options, but these are going to be the most common for this type of work, using your buffers or your sample prior to purification or maybe that sample application. The pore size is critical to select well in that the typical contaminants that you may come across at any stage in the purification, these pore size ratings were designed and developed to eliminate. So pre-filtration, if you do have a lot of inclusion bodies or other large aggregates, a pre-filtration filter will allow those larger contaminants to be removed before a final filter layer can allow proteins and other molecules of interest to pass through it. Clarification, if we're looking at maybe cell lysis or debris, as Karen had mentioned, you might want to go with a larger pore size to make sure that that clarified product or partially clarified product can be easily loaded onto your column. We also do have sterile filtration considerations and sterile filtration with mycoplasma reduction. So a 0.2 or a 0.1 can be used if that is the goal of your application. So selecting the correct pore size should match up to the expected or anticipated contaminants that you would have of either your sample or your buffer, and then just choose the correct or best pore size to use. Filtration volume really comes down to surface area. How much volume do you need to pass or flow through that filter to have enough of filtrate, that would be that liquid that has come through the filter, we'll call that the filtrate, to make sure that you can perform your chromatography run or your sample load. As you can see here, there are suggested sample volumes, and I use the term suggested and guidelines maybe. Every sample is different, and only you truly will know the best filter for your sample. You may be able to do a quick research experiment and use a filter, a smaller one and a larger one, run both samples, and just look at the results. Is it impacting your results? Are you getting better or worse? And that will guide your decision. But typically for syringe filters, if a 13 millimeter syringe filter usually has a sample volume of up to or less than 10 mLs. If you need to go up to maybe 100 or 150, you can see there are 25 and 32 millimeters. And then down the line for larger syringe filters, or what we would consider a filtration disc, which would be a much larger volume, up to about 3 liters. The typical holdup volume. Now, what is holdup volume inside of a filter? You have many different pores and openings and crevices inside of any filter unit. And as your sample buffer or your liquid buffer is flowing through that filter, holdup volume refers to the amount of volume that is left inside of the filter after the filtration has completed. Now, there are strategies to try to extract or remove some of that holdup volume. There's also some risks. You may rupture membranes, therefore causing your filtration to really just not happen, which we don't want. You want to make sure your samples and buffers are filtered. But if this typical holdup volume is something to consider, and how you would consider that is just assure that you have enough filtrate, again, that volume that has come through your filter, available for the work that you need to perform, either running those buffers through your system or applying your sample through a loop or a sample pump. Just make sure that you have plenty and can have some loss of a filter due to this holdup volume. If the amount of loss is more than you can tolerate or more than you actually have sample physically to use, consider using a smaller size filter diameter. And then lastly, the right filter for your application, membrane. And again, each of these 4 pieces here, is one more than important? Maybe, but usually they all work in tandem, in concert together. You may need to do several trials or runs. What we are showing and selecting here for typical protein purifications, these are what work for many. You may need to trial them, or maybe try a cellulose acetate and a polyether sulfone. Try both again. See if it works better or worse with your molecule. Let your sample biology be the determining factor, not a manufacturer, but we are here to provide options. And as you can see, that all of these filters are hydrophilic for protein purification. We're usually working in that environment. And then they all follow the same protein binding. If protein filtration is the goal, we want to have that binding or the adhering of loose proteins to the filtration matrix. We want to keep that low. Same thing with DNA, and then pH compatibility. Depending on which step of a purification workflow you're in or what pHs of the buffer, we always want to assure that both the sample and the buffer pH are compatible with the chromatography or the filtration media, and chromatography media for that matter. They sort of all do work together. So membrane types. We offer many different membrane types at Cytiva. For protein purification, I would definitely agree that these are probably the 3 most considered and used among our customers. Effective filtration area, or what is known simply as EFA, I like to say that is the business end of a filter. That's the true surface area that you would have that can be exposed to the buffers or to the samples you're going to pass through. And as you can see here, it's a direct correlation to filter size. The larger the filter diameter, the larger the effective filtration area. Filtration area, it does correspond to sample volumes, but again, these are suggested or recommended volumes. You may notice or be able to achieve more or less filtrate, again, depending on the pore size that you selected, but more importantly, your buffer or sample composition. If it has more particulates, filters do tend to clog more of the pores a little bit quickly, and you may reduce or notice reduced flow or reduced filtrate. So again, if you're not getting or you're not achieving the amount of volume after filtration, consider extending or selecting a larger size filter size, which then therefore will have a larger EFA.
Thanks, Dan. Hi, everyone. The next few slides, we're going to be looking into ultrafiltration. So ultrafiltration is really used pre or post purification, and it's designed to concentrate, buffer exchange, or desalt your sample. We use ultrafiltration membranes to achieve this. Ours is a PES that Dan was talking through earlier. Its brand name is called Omega. There's also regenerated cellulose available on the market. Now, compared to alternative techniques such as dialysis, precipitation, lyophilization, ultrafiltration is really gentler to the molecules. It doesn't require an organic or extraction, and it doesn't alter any ionic or pH conditions. It can be performed at lower temperatures, so in a cold room, but this will affect its speed. It will be slightly slower. And finally, it is both fast and also relatively inexpensive. In the Cytiva product range, we have, In the Cytiva product range, we have the NanoSep, which is a 0.5 ml device. We have the MicroSep and the MacroSep. These are a 5 ml and a 20 ml device, and the JumboSep, which is a reusable 60 ml device. What we can then also do using the same Omega membrane is scale up to the Minimate system. So Minimate uses tangential flow, or you may have heard of it described as cross-flow filtration, and it's essentially using the same ultrafiltration membranes, but in different filtration technique. With our spin devices, we use something called a dead-end filtration, where the direction of flow is the same as the direction of filtration. So it starts off very fast, very good for low volumes, but can slow down quite quickly if you're targeting large volumes through it. The TFF system, cross-flow, is slightly different, where the direction of flow isn't the same as the direction of filtration. So this just means that the filter blocks a lot slower and it can achieve much higher capacities. Let's go next slide. The most important thing in ultrafiltration is to select the correct molecular weight cutoff. Now, molecular size of your biomolecule is the most important consideration here, but other things such as molecular shape, charge, conditions, and sample concentration will also impact its molecular weight cutoff selection. So it's a good guide, but it's not 100% foolproof. Now, the first thing to understand is molecular weight cutoff. So this isn't a pore size like 0.2 micron or 0.45 micron. It's more of a nominal retention rating. So we target a standard molecule of a known biomolecular weight, and it has to retain 90% or above. And that's where the standard 90% protein recovery comes from. For our recommendation, we recommend a molecular weight cutoff that is 3 to 6 times smaller than the weight of your biomolecule. So if you've got a 90 kilodalton protein, a 30 kilodalton cutoff would work nicely. And if you've got a 150 kilodalton antibody, again, use a 30 kilodalton molecular weight cutoff. This recommendation does vary manufacturer to manufacturer. So ours is 3 to 6. Others out there, like the Viva Spin, is 2 to 5, and the Amicon is 2 times. So this is something to really be aware of if you are looking at alternatives or trying to test 2 devices together. Really don't use the manufacturer naming. Use your biomolecule weight and use the molecular weight selection guides that are available to make sure you get the right product for your biomolecule. Do you want next slide? Once you've selected your molecular weight cutoff, the other things to really consider here are device design and then some other considerations that are a little bit more varied. This is to really optimize. So molecular weight cutoff is the most important thing to make sure your concentration, your buffer exchange, your desalting step is effective. But this will take you to the next level and make your concentration a little bit better. The first thing to consider is final concentration, your dead stop. So every device out there will have a slightly different final concentration volume that they can get to. And this is really important. Number one, you need to make sure that it's going to achieve what you're looking to achieve. So if you're looking for a really low concentration, make sure you're using a device that achieves it. But also make sure that you don't over concentrate. So if you're not looking to concentrate too far, don't use a dead stop that's really low, as you've got a chance that if you do forget about it for an extra 5-10 minutes, you may concentrate too far. and you may have issues with sample aggregation. Final thing here is if you're looking at dead stop, there are products out there, including our nanosep and the microsep, where you can essentially select a dead stop. You can select your final concentration volume. And the way you do this is use our concentration calculator, and you add a set amount of buffer into the receiver part of your tube. This will essentially stop the filtration at a certain concentration factor, ensuring that you don't overconcentrate and you don't risk your sample integrity. The next thing to look at for design of device is the aggregation caused by concentration gradients. So there's two main designs out there, a V-shape and a vertical paddle. Now, a V-shape concentrates very low, but it does risk a concentration gradient. And this is really well seen in the bottom of the V, where you've got a really viscous blob of usually overly concentrated protein. And at the top of the buffer in that V-shape, there'll be very little protein. The vertical paddle in the microsep, the macrosep, tries to prevent this. So it has a much more homogeneous sample, and it really prevents this overconcentration found at the base of the V. The slight trade-off is it can't concentrate as low, so it does depend on what you're looking to achieve with your sample concentration. Other things to look out for are materials of construction. There's two main types, there's polypropylene and there's polystyrene. And it's a choice of how you want to perform your concentration again. So polypropylene is what we use, and it typically is used throughout all of life science because it's very low binding. The alternative is a polystyrene, so it's slightly higher binding, obviously still very low binding, but also is clear, so it has a much better clarity. So if you're looking to visualize your sample, it may be easier. Again, it's down to user experience and how you want to perform your concentration. And then looking at the membranes themselves, they are often, well, they're always loaded with preservatives. These preservatives and wetting agents really protect the membrane during transport and storage, and they maintain pore integrity, so they have to be there for membrane quality. It's really recommended to precondition by removing these preservatives using DI water. Other considerations number one will be speed. So speed will vary manufacturer to manufacturer. A lot of it is design-based, membrane-based, and just how your biomolecule interacts with the device. But also molecular weight cutoff will come into this. If you use a molecular weight cutoff, say for us, our closer to the 3 times recommendation rather than the 6 times, it's probably going to be faster. It's not always the case, but it's a good rule. The closer to the 3 times, it will be faster. Quality control, these obviously undergo a lot of quality control, but also as part of your test, you can ensure that your test and your concentration is high quality by testing multiple options, different manufacturers, different molecular weight cutoffs to make sure you get to the result that you're looking for. Recovery. In order to really maximize recovery, similar to what you do with the membrane preservatives and removing them, you can do a rinse step with your buffer. This is really good to reduce non-specific binding, especially if you've got a really low concentration sample where any loss of sample is going to be noticeable. The next thing to look for is, as Dan was mentioning, in terms of volume, make sure you get the device that is suitable for the volume you're looking for. If you're looking to put 0.5 ml through a 20 ml device, it's going to lose a lot of sample. It's not really a good use of that device and your time and your budget. And the final 2 things to look at there are budget and time, and they're very much linked. And this is the decision of where you scale up from centrifugal filters to minimate the tangential flow system. Obviously, there's extra cost in buying a new system, but if you're doing hundreds of mils up to liters of sample, this will provide a much simpler and a much faster way of concentrating buffer exchange and desalting your sample. So that's really a consideration of what your kind of samples your lab is processing at that time. Can we go to the next slide? So thank you for your attention during this webinar. We hope you've really found it useful. Filtration, we hope we've shown, is a really integral part of the purification workflow. It's involved in sample clarification, protection of your equipment, prevent it clogging, buffer exchange, concentration, and can also sterilize your final product. So it's a really important step that sometimes can be misunderstood. It enhances your protein purification process, and it will make it much less likely to go wrong. So we've shown a lot of filtration products out there. Filtration is what we specialize in. So please don't hesitate to ask any questions, and thank you for your attention.
Jake, thank you for taking us through that. For this webinar, we did want to end with maybe one final new product. As you can see, there's many options for filtration inside and pre and post your chromatography runs. We understand that the amount of choices and selections you have available from many different vendors that offer such products, it's vast. We've also heard from our customers that the time it may take to select the proper filter for your specific chromatography run, it's just time you don't really have, or you can use that much better. So what we have created at Cytiva is now the Cytiva Protein Chromatography Sample and Buffer Filtration Starter Kit. Not only do we give you an extremely long name of a product, we give you great options inside this kit. So as you can see, in this starter kit, there's over 16 different filters. Now, these are the filters that we have mentioned during our webinar today. You have your different centrifugal filters in there, syringe filters, larger capsule filters. We also have straight membrane circle filters if you wanted to do large scale buffer filtration. The membranes in here are the exact ones that we've talked about and presented during the webinar, and we hope that this starter kit would be a beneficial resource for you in your lab. Talk to your local ECTA sales specialist, your local lab filtration sales specialist, your account manager, any of your local representations from Cytiva. It is part number 2977, and the goal and reason that this starter kit was built is just to make those selection of filters for your protein purifications that much easier and simpler, and therefore we put it in a nice handy starter kit that is available as of now. If you do need more support, again, knowledge is power, and at Cytiva, knowledge is one of our best products, and we're very happy to support and help you, whether it's your filtration, it is your purification, how the products work, how the products need to be selected, whichever support you would need. You can always at your call on scientific support. You can see that we have many different support centers around the globe. These are listed here on the slide. Just a simple email into that email box will directly get you in touch with a scientific researcher here at Cytiva to begin your discussion and hopefully get you the support that you need. And with that, I do, on behalf of myself and my colleagues, do want to say thank you for your attention. Karen, Jake, it's been a pleasure to present with you today. And at this time, we'd be happy to take any questions that you have.
Well, thank you so much for that presentation, Dan, Karen, and Jake. If you do have any questions for our presenters, then please continue to submit them using the Q&A button at the right-hand side of your window. Unfortunately, I couldn't make it for the Q&A section, but I'm joined by Lars leads the EMEA training and application team at Cytiva and has over 20 years of experience working with active systems and protein chromatography products. So we will now begin to address some of your questions. So the first question I'd like to get to is, how do you select for the correct MWCO?
Sorry, I didn't hear that question there. There was a bit of background noise.
Sorry, so the initial question is, how do you select the correct MWCO?
Ah, gotcha. Okay. So the molecular weight cutoff. The short answer is, as much as possible, try and follow your manufacturer's suggestions. So our guidelines are 3 to 6 times smaller than your target biomolecule of interest. These are always guidelines. So the molecular weight size is probably the most important angle of selecting the molecular weight cutoff, but other things such as charge, the actual shape of your biomolecule, so linear or globular proteins have completely different interactions with the membranes, and operating conditions and sample concentration as well. So the short answer is follow the guidelines. Longer answer is follow the guidelines, but also test a couple of options, so different molecular weight cutoffs at the top end and the bottom end of the guidelines, but also other membrane types as well. So don't just restrict yourself to the one molecular weight cutoff, the one supplier, or the one membrane type. If you're talking, Tristan, you are on mute.
You're on mute.
Sorry. So the next question is, my protein is valuable, expensive to produce, and takes considerable time to obtain. I'm concerned that filtering it will result in a loss of volume that I cannot risk. or any minimize.
Okay, I mean, it was low from you, Tristan, but I think I got the key points of the question. I'm just going to repeat that back. Maybe give me a head nod if I do have all the key points. But protein is expensive. You're limited on the amount, and you're concerned that filtering may cause an unacceptable loss. Was that the nature of the question?
Yeah.
Okay, yeah, and I mean that's a real concern as protein titers continue to go up, and the sources of where we obtain these proteins from, it's constantly research is a battle of finances, right? And understandably that if it takes you weeks or months or days, depending on how long that extraction period might take, eventually you get to a protein that's just so expensive, and you're now concerned. I have to keep all of it. It's real world. I'd maybe take the question slightly different though. What is the cost of maybe not filtering? Is this something new you're placing onto a column? How is it going to react? Is it going to crash right out? Is it going to precipitate? I think a lot of things can happen either way, either good, bad, intended, or not expected. With filtration though, filtration is really designed to remove particulates that can inhibit purification down the road, or it can cause you more issues as you go on to a chromatography system and purify. So usually the benefit of purification or purifying that sample usually does outweigh any risks. The one though, two I'll possibly maybe just touch on briefly. Size. You talked about size, I believe, in the question, or how much volume. Do not just think that the industry standard is 25 millimeter syringe. I don't know where that came from. I'm in this industry. I've been in the industry forever, and it's batted around that a 25 millimeter syringe is what you should be using. No, not at all. Maybe you only have 1 ml of sample. If you have a lower volume of sample, use a smaller diameter syringe filter. What will that do for you? Every time you use the smaller diameter size, it's the amount of flow path that goes through there, that dead volume. You're going to minimize that dead volume. You could also use a strategy after you filter your sample is to take that syringe and put a little bit of air in and just very gently use a little bit of air. Apply that to the syringe filter. Again, you want to press any of the liquid remaining in the filter out so that you can obtain it all and inject into the system. But if you just slam that membrane with force and hit it really hard, you have a chance of rupturing the membrane. Once you rupture the membrane, everything that was held back, well, now that's all coming through. So I would say that's probably the number one strategy, I would say, if you have limited amount. The other one, I mean, may be, Jake, instead of using like a syringe filter, if the volume is small, could you go to maybe a centrifugal filter?
Yes, you can. Our 0.5 ml device, I think, has a hold-up volume of, you're talking 1 or 2 microliters.
But we also heard an alternative in Karen's talk, right? So centrifugation could be an alternative, and I definitely understand this type of question coming from out of my research time, out of NMR structure determination, where you have samples that are very, very valuable, and where you do not even want to lose 1 or 2 microliters because it was so costly to produce them, and therefore, in those kinds of scenarios, centrifugation with, as we heard, 10,000 or even up to 50,000 G for some minutes is a very nice alternative that definitely keeps all your sample available.
Fantastic. We've had a small technical queue about the webinar coming through about volume and audio. We've done some internal tests. Everything's working on our side. So if you are experiencing any issues with not being able to hear, then please refresh your page, and that should be able to or check your own audio connections. So another question that's come through is, what is the optimal protein concentration that should be maintained to prevent aggregation?
There's not a clear answer to that, to be honest, because that is fully depending on the type of protein you're working with. Yeah. So when you think of membrane proteins, you you just look at them and they already start to aggregate, where others are highly soluble. So there's not a clear rule to that.
And just to add to that one, obviously each device works slightly different. So there's a real theme here, which is test a couple of options. Different formats, different structures of device will work differently. So our vertical paddle has a more homogeneous one, so you may not get the over concentration. So hopefully that should reduce aggregation, but it is one of those things of test.
And then does the buffer need to be filtered and degas before using active system, and how important is it?
Yeah, I would agree. I mean, I see a couple head nods going here at Lars as well. I think absolutely. These are systems. They're higher pressure systems or lower pressure systems, but they're contained systems. And the containment is in the valves, in the tubings, into the columns of which your sample is going to go through. Any other particulate that is in that fluid path, it can damage, it can complicate, it can ruin results. Usually it's nothing good that having extra particulates in your system. Unless anyone can maybe put in the chat a good reason to have particulates, I don't know of any, and I've done, these types of systems for years and years and built a career out of them. So yeah, I would absolutely say filter your buffers. Is it critical? Yeah, it can be. It all depends on the environment that you work in. Are you working inside of a deli fridge, a cold box, a storage room? They usually have large fans regardless, just to keep the humidity down in those. That large fan spinning around is whipping up dust particles and everything else into the air and into the environment. Where's it going? It's going into your buffers. So filter them, parafilm them, cover them. I would say it's absolutely mission critical.
And for the second part of that question about degassing, I mean, very often when you do a typical kind of buffer filtration, then you also degas it at the same time. But when it comes to degassing and thinking what kind of influence does a lot of gas dissolved in your buffer has to the system, it actually typically accumulates in the pump. And typically, you know that when you have a very freshly prepared buffer where you just took the water out of the tap, prepare your buffer, put it onto the system, it just takes some minutes that you realize that there is bubble forming in your inlet tubings, and that kind of air is actually then accumulating in the pump, and then the pumps are not able to deliver the flow rate that they actually should run with. Yeah, so that is something that I mean, you can prevent this by, let's say, preparing your buffer in the evening, let them stand overnight, and then at the next morning, most of the gas has disappeared. But as Dan also said, it's a mixture of filtration and degassing, and that's the easy way. Yeah, so use it.
Okay. And then another question that's come through is, I purify many different types of proteins and antibodies. What is the best membrane to use for proteins?
So that can go a couple different ways. Jake, do you want to maybe take a stab at that from a concentrator?
Yeah, I will. So in the concentration step in centrifugal filters, there's two membranes to pick from, PES and regenerated cellulose. So they do the same application. They have the same namings. They're all done in molecular weight cutoffs, but they're inherently very different. Different polymers, different manufacturing techniques, different quality control throughout the whole process. So they're very different. And then it essentially comes down to a bit of luck. If your protein interacts with one membrane, it might not interact with the other. They're both perfectly designed for protein work, viral work. They're both really low binding. They both have good 90% recovery and more. It comes down to your sample at the end of the day. And this is the advice we would always say is, do try both. You may see no difference. You may see huge difference. And you often speak to a lab where one membrane type is preferred over the other due to one experiment a few years ago. Don't just restrict to just using the same membrane type. Do make sure you test each type out there. They are so different.
It's good to hear that, Jake. So the converse, though, is, if you were looking at a little bit larger sample prep, in a syringe filter, we have many more than two choices. So maybe a little bit more legwork, a little bit more research. Believe it or not, Cytiva has, I believe, the most available membrane types that you can purchase and look through. It's a very wide, broad portfolio. That's a great thing. What's the challenge? Which one do you use? Where do you start? Each of the membranes that Cytiva offers does have characteristics unique to its manufacturer, to its properties. You would want to select that based on your chemical compatibility. When we're talking protein purification, though, you're usually using, some type of a salt buffer, some type of a neutral pH. So I would agree, PES, PVDF, RC, cellulose acetate, they are some, key membranes that are used by the majority of the market. You always have people that do different for their own specific, and we would always encourage that what is best for your protein, not so much what product is best, but how does the biology work. But you just want to be, it depends on how many different proteins you're working on the lab. If you're more of a core lab, or have different samples coming in every day, then having more of a general protein or a membrane that can do a wide variety. One of the newer ones that is in the offering at Cytiva is a hydrophilic PTFE. So it's very wide, broad chemical compatibility offering. It's very similar to RC and PES in that it has a low protein binding threshold, but you can use and just throw just about any buffer at it. So again, what is the goal? If you have lots of proteins, do they all have the same pHs? Do they all have the same maybe sample buffers and matrices? Start looking at what is the pattern or what are the makeup of each of your buffers and your samples, and then you can almost assign different types of filters or membranes to work. The goal would be, though, is you don't have to choose from 12 filters every time. That just is going to complicate your lab and make your life that much harder. Most membranes can be used multi-platform or multi-use, multi-buffer. Try to find the ones that offer you the limited choice so that you're just not stuck with multiple options on every run.
Fantastic. And then another question to come in is for perfusion, is hollow fiber or cassette, which is the best option?
Not. I think that might be a tangential flow filtration question. In which case, my knowledge is a little more limited on that one. That might be a question we come back to you on.
It might TFF. I can speak and I understand that, but the complication of adding the perfusion to it, Lars. Unless there's anything else that you might know about that one, we might have to get back to you on.
No. So from my end, I know that this comes out of the cell culture stuff, but that's not my level of expertise.
True, using Cyta something. Yeah, okay. And whoever asked that question, we, even if we don't on the collective call here have that answer, we do want to get back to you. So if there's maybe another way you could ask that question, please do. If not, as long as we have contact details, Tristan, we'll be able to follow up with some answers after.
Absolutely. Right. I think that might be. There's another one question which is for. And so verbatim, the question is autoclave membrane or gamma irradiated, which is good for use?
It depends on the membrane. This is dredging up some membrane information from a while ago. A few are fine with it, but most aren't. So, for example, the centrifugal filters and the filter plates that I'm a PM for, you can't autoclave them. They can be gamma irradiated. A problem with autoclaving is a lot of times when membranes either aren't stable at that temperature, or if they get wet and then dry, they become impermeable. They become hydrophobic, so you can't get your sample through. Gamma irradiated is always top if you're sterilizing a filter. ETO is sometimes used as a gas, but autoclaving is the least common way of doing it. So I would always say gamma irradiated if possible.
Mm-hmm.
Fantastic. Well, thank you very much, Dan, Lars, and Jake, for answering our questions today. Before we wrap up, do you have any last comments that anyone would like to add?
No. Thank you very much.
Appreciate the time.
Brilliant. Well, I would like to once again thank our wonderful presenters, Dan, Karen, Lars, and Jake, as well as you, our listeners, for your time and questions. You'll receive an email with how to watch this webinar on demand shortly. Don't forget to visit us at www.biotechniques.com for more webinars. Thank you again for attending, and goodbye.